going to point to you, you're going to go crazy, and we're going to bring out Zoe Wyatt. Are we ready? 1, 2, 3, go wild and crazy!
Hello, hi, my name is Zoe Wyatt. I'm doing a PhD in mathematics. Yes, stay calm. I've got 99 problems and they're all maths ones. So I'm actually approaching the end of my PhD thesis and I keep putting things off until after I finish. So for example, I really need a new phone after I finish. I should sort out my bike brakes after I finish. Actually, it'd be quite nice to have a stress-free, positive outlook on life. Definitely after I finish. PhD's in the house there. So I'm a mathematician, but I study problems coming from physics. And I love looking at the world around us, at things like phones and bikes, and seeing how maths and physics can explain these things. So I was laughing recently because there's a competition in Glasgow and also worldwide called the 3-Minute Thesis Challenge. And the idea is to explain your thesis in 3 minutes in layman's terms. Now, I didn't enter because 3 minutes isn't enough time to make many jokes, but one of the rules made me laugh, and it said you're not allowed to bring in any props or experiments on stage. So if I were to compete, I'd have to go up and say, "Excuse me, before I begin, would all the electrons please leave the room? I think we need a new, more positive atmosphere in here." Just checking you got that one. Neutral parties can remain. Okay, so what do I study? So I've recently been studying something called the electroweak Higgs theory in particle physics. Okay, so let me explain this to you. So electro stands for electromagnetism. Okay, this theory describes how electrically charged particles interact with each other. It was actually developed by a Scotsman, James Clerk Maxwell, in the 1860s. And so this tells us, for example, how a negatively charged electron is attracted to a positively charged proton inside the nucleus of an atom. So that's electro. So the next part, electroweak. So weak stands for the weak nuclear force. So we could call it the weird nuclear force. This is a funny one. So this describes how particles with a different kind of charge, something called a weak hypercharge, how they interact with each other. Okay, so things that are weakly hypercharged are things you know, like electrons, quarks, protons, those kinds of subatomic particles. So the weak nuclear force, to give you an example, it appears in our understanding, or it explains how the carbon-14 atom decays into nitrogen-14. Okay, this process is a weak nuclear process, and our understanding of this, very much underpins our knowledge of carbon dating, which obviously we use to date things like fossils, plant material, and Prince Philip. So, speaking of acceleration, when you accelerate electrons, they become excited. That is a technical term. And these excited electrons cause a perturbation in the electromagnetic field, and this produces photons. Okay, similarly, when I accelerate these weakly hypercharged particles, this causes perturbation in the weak hyperfield, and this produces other particles. It can produce 3 types of particles, the Z particle, and 2 types of W particles, the W plus and the W minus particles. Please don't freak out, there is not going to be a quiz. The main thing to take home is that these weak nuclear interactions produce these ZW particles, and those are my initials, so you will never forget that now. Okay, now while the photon is massless, these ZW particles are massive. They're really heavy, like 160,000 times heavier than the mass of the electron. Okay, so physicists and mathematicians wanted to understand where does this mass come from? And this is where we need the last ingredient in our electroweak Higgs theory. We need the Higgs particle. Now, I'm sure a lot of you know about Higgs particle. It was discovered in 2012. It's amazing what you find under the sofa these days. So the Higgs particle is heavy, very heavy. That's why it took so long to find. Did anyone get that? Yeah, that was a factual statement. So the Higgs particle is very heavy, and consequently it's very lazy. Yeah, it likes to hang out in this low energy spot, not really doing much, and we call this the ground state of the Higgs. Now the ground state of the Higgs has a very special property in that it is symmetry breaking. Okay, what is symmetry breaking? Unfortunately, unless you're a supermodel, it's your face. It's not perfectly symmetric. But the symmetry breaking of the Higgs is very special because it explains why these ZW particles, when they interact with the Higgs, they get their mass. But because the symmetry is broken, because it's not perfect, one particle remains massless, and this is precisely the photon. Okay, so this electroweak Higgs theory has been tested to really high precision at the Large Hadron Collider in Geneva. It's led to heaps of Nobel physics prizes. Yeah. So what do I do as a mathematician? Okay, something a bit more theoretical. So I mentioned that the Higgs has this ground state, this low energy spot it likes to hang out in. And indeed all the particles have this, this kind of low energy spot they like to live in. And we call this the ground state of the theory. So my goal is to show that the ground state of this electroweak Higgs theory is attractive. We have good words in maths too, purely naive, but good words. So what does attractive mean? So that means that if I perturb my particles slightly away from this ground state, and if I evolve them according to the equations of motion of the theory, I'm interested in showing that they naturally tend back to this ground state. This ground state attracts these perturbed solutions in. Now something else which is slightly subtle is I study the classical deterministic theory. Okay, so let me give you an example. So two of the main attractors in my life are German beer and my German boyfriend. I will leave you to ponder which one came first. So if I am 10 kilometres from a bar that serves German beer, it's unlikely I'm going to go there. But if I'm 10 metres from a bar that serves German beer, you could probably prove that I'll go there. However, deterministic theory says that whenever I am 10 metres from a bar that serves German beer, I must always tend towards that bar. Okay, it's determined by this initial condition. So this is great for my alcohol consumption, not so good for my boyfriend, and as you can tell, it's quite restrictive. So that's classical determinism. Now, some of you out there, maybe some of you remember from high school physics, or more likely from Marvel Ant-Man. They're like, but what about the quantum world? And you're very right. Okay, well, I'll explain why the quantum world is relevant, but something interesting in quantum theory is this classical determinism goes out the window. Okay, things become probabilistic. And the reason for this is something called the Heisenberg uncertainty principle. And this basically says that the more precisely you know the position of a particle, the less precisely can you know its momentum, and vice versa. Okay, momentum is a measure of mass times velocity. Okay, so it's quite a weird thing. This is a quantum effect, you don't see this on the macroscopic level, but I like to think that it answers the question of why quantum physicists are not good at sex. Because when they find their position, they lose their momentum. And when they get up their momentum, they can't find their position. My boyfriend's a quantum physicist, and that joke was not intended at him. Okay, so it turns out that this electroweak Higgs theory that I've talked to you about tonight has been mainly tested experimentally using methods from quantum theory. Okay, so there's a very valid question. You can now say, well, what's the connection between this classical deterministic result and this quantum experimental world? Now, there are some limits you can take, some kind of low energy approximations you can do to make sense of one in terms of the other. But by and large, it's actually still an area of active research. So I think the full answer to that question, I'm going to leave until after I finish my PhD. Thank you for listening. I've been Zoe Wyatt.